Right. So today's basic topic, I want to get this chair out of the way. Right. Today's basic topic is essentially about, well, the title of the note is computable and computably enumerable sets. But I want to, rather than starting off immediately with the definitions, I want to motivate it a little bit informally. So what we're basically going to talk about today is notions of computability for subsets of the natural numbers. So the computability, essential content is going to be that computability notions for subsets, or if you like, sets of natural numbers in other words, subsets of sets of natural numbers N. Now, it almost goes without saying that a lot of computational problems of interest can be captured as problems about sets of numbers. So lots of computational scenarios where we have different kinds of data. You can represent the data as natural numbers, and you're often interested in some collection of data that satisfies some property, so that can be defined as a set of natural numbers. So I'm not going to go into too many examples, well, into any example along those lines, but you should immediately be able to think of some. Also in mathematics, sets of numbers play a very important role. So let's maybe look at some examples from mathematics, but I don't want to spend that long on examples. But some important sets of natural numbers in mathematics, I'll say, for example, a set of prime numbers. So this has been a source of fascination for mathematicians since the ancient days. So already the Greeks were fascinated in prime numbers, and it is still a source of fascination to prime numbers now. So several recent Fields medalists have gone to people who have made major contributions to the study of prime numbers, including one of the Fields medals of this year that went to James Maynard from the University of Oxford, who's been advancing humankind's knowledge of prime numbers. So that's a set we're all used to. Still has a lot of mysteries in it, but anyway, it's a set of natural numbers of interest to mathematics. Something a bit more fancy would be, based on this, would be the set of numbers that occur infinitely often as, well, I'm going to base it on prime numbers as what are called prime gaps. So prime gap is the distance between one prime number and the next prime number. So the first prime gap is 1 between 2 and 3, the next prime gap is 2 between 3 and 5, and 2 between 5 and 7, and 4 between 7 and 9. And you can consider this as a perfectly good mathematical description of a set of natural numbers, those numbers that occur infinitely often as prime gaps. So it doesn't take much mathematics to see that any number in this set is necessarily even. On the other hand, it's actually rather difficult to see that any number at all exists in this set. So this was a fact that was only proved in 2013 by an American mathematician called Zhang of Chinese descent. It was a major result in number theory. So he established the first finite bound on prime gaps, and the consequence of his result is that there does exist a number that occurs infinitely often as a prime gap. And currently it's known that there exists such a number less than or equal to 600. That's the best that's known. The very famous twin prime conjecture that goes back to ancient days about whether or not there occur, well, that conjecture is that there occur infinitely many primes where the prime gap from that prime to the next one is 2. But nobody knows the answer to that. So with this set, we don't know. We only knew that it was non-empty in 2013, and we don't even know if we know some basic properties like any number in it is even, but we don't even know if the number 2 belongs to it, although it's conjectured to belong to it. In fact, every even number is conjectured to belong to this set, but nobody knows. So the points of this are twofold. One is sets of numbers are interesting things in mathematics and throw out difficult questions, and some sets are more complicated than others. I also want to use these examples to consider another way of thinking about how we might talk about sets. So the sets of numbers are going to be somehow interested in the computability property of sets of numbers. There are essentially 2 different things we might want to do. So we might consider sets of numbers from 2 different viewpoints. So one viewpoint I'm going to call testability. And testability is, can we test whether a given number is in the set? If we go to our 2 examples here, prime numbers, give me a number. I can indeed test whether it's a prime number. There are various algorithms known for that. A very efficient algorithm actually only tests up to a high probability of success. That's one of the nice things. That's a very nice example in the theory of algorithms in computer science. But it's known there is an efficient, in the sense of polynomial time algorithm that actually tests definitively whether a given number does belong to, it is a prime number or not. So we can perfectly well test membership of a set of primes. Whereas, as you can imagine, it's very hard to test membership of this set. I mean, we have to check something occurs infinitely often, and we don't even have much of a mathematical handle on it. Although if we ever manage to prove the conjecture that every even number does indeed occur as prime gap infinitely often, then it will turn out that this set is very easy to test, because actually it might just be the set of even numbers. But for the moment, this set we can test, and this set we don't know how to test. So that's one handle we might want to get on the set of natural numbers. Another handle I'm going to call generativity. And generativity is about, can we generate elements in the set? So can we systematically list? We might be talking about infinite sets, but can we systematically list, perhaps with repetitions, the elements of the set? So can we generate an exhaustive list? And we put exhaustive in brackets because one might also consider weaker notions of generativity, in which one's just able to generate sufficiently many elements or something like that. So can we generate an exhaustive list, essentially infinite list of elements of the set? Again, in the case of primes, we can do that. I mean, you can just go through the numbers testing if each one's prime if you want, and throwing out those that aren't prime, but there are other more sort of efficient methods of you don't need to go through a prime test to do that. Sort of sieve-based methods, as they're called, based on also the ancient Greeks. Aristotle's sieve gives an algorithm for doing that. And here again, of course, we've got the difficulty because we don't even know where to get started. We don't even know if 2 is the number 2, is it? But anyway, there's these 2 facets of sort of being able to compute with the set. Can be testable membership, and we generate elements. And you might already get a feeling, and even the feeling can be based on precise foundations, and you might be able to already see, some of you might be able to see somehow there's a connection between these 2. So somehow it turns out the sets we can test are somehow the sets we can generate, and depending on how well we want to generate the sets, that corresponds with how well we can test sets. So that's going to be the subject today. We're going to look at essentially 2 notions of testability and see that both those notions are characterized in terms of generativity properties. Okay? And the 2 notions of testability are ones we've already met: decidability and semi-decidability. So the primes is a decidable set. We have a yes/no algorithm that tells us, given a natural number, whether it is prime or not. The set of numbers that occurs infinitely often as prime gaps, we don't know. If it's the even numbers, then it's a decidable set, but from this description, it might not be a decidable set. We don't know, and it's almost certainly not a semi-decidable set either. I mean, unless it turns out to be the set of even numbers, which it probably is. Right, so the 2 notions we're going to look at with regard to testability of sets are decidable sets of numbers and semi-decidable sets of numbers. So we already have definitions for what these mean. So the first definition of decidable set and semi-decidable set of numbers in lecture note 3, where we have the notion of representation. For any represented set, I define what it meant to be a decidable subset of a represented set and a semi-decidable subset of a represented set. We already have those notions. On the other hand, it's so fundamental that I'm just going to give you a direct definition now of semi-decidable and decidable subsets of the natural numbers. And also, to be in keeping with most of the literature on the subject, we're going to start using a different terminology from decidable and semi-decidability, but the different words are interchangeable. So we're going to have 2 kinds of sets. The decidable ones we're going to start calling computable sets. So a set of natural numbers. Let me just in my note is decidable, and we're now going to call it. Well, I'm still going to use the word decidable, but computable or equivalently decidable, or the people used to say recursive. The terminology computable versus recursive is kind of it's a division that runs through this subject. But this course is called computability theory. People used to often call it recursion theory, and some people still do call it recursion theory. And then people will talk about recursive functions, and various use the word recursive, and recursion, and so on a lot. So there's a modern tendency towards computability, so I prefer that version. So basically, we're going to mean a decidable set of natural numbers. I'm going to keep the word decidability in this course for decidable sets of data different from natural numbers. Only in the case of when we're dealing with the natural numbers that I'll use the word computable set, because it's so pervasive in the literature, or well, either computable or recursive, pervasive in the literature. That's a natural number. Anyway, a set A of natural numbers is computable if, and I'm just going to repeat the definition from lecture 3. So if its total characteristic function pi sub A characteristic function, so remember this is the function that maps an x to it's a total function. So it's the indicator, also known as the indicator function. So to 1, if x belongs to A, so it's simply it's a Boolean test. 0 if x doesn't belong to A. It's computable. It's the same idea we've had throughout the course. Decidable means we can test membership getting a yes answer a 1 or a no answer a 0. So this is instantiating the definition via representations, but representations essentially go out and completely not needed to make the definition, because we simply, in order to understand this definition, all we need is to know what it means for a function from natural numbers to be computable. This is a total function from natural numbers to natural numbers, and we're asking the set is decidable if this function is computable. That's the definition. Sorry, it's decidable, or other words, computable. And then we make a similar definition for semi-decidable. And the new terminology for semi-decidable is a bit of a mouthful. It's computably enumerable. So a set is computably enumerable because that's a mouthful. It's often just abbreviated CE. Computably enumerable is a synonym for semi-decidable, or for old terminology, again, computably is replaced by recursively. So old literature, meaning literature from the previous century, is tend to be called recursively enumerable. And again, following the pattern of lecture 3, where we define semi-decidability in general for representations, we ask for its partial characteristic function. So this is pi, it's chi superscript d, subscript a. And remember, this is defined by the partial characteristic function. So this, we apply it to a number x. Now partial, so we need a Kleene equality. And it's again 1 if x belongs to A. But we ask for it to be undefined if x doesn't belong to A. So it agrees with the idea we had at the beginning of the course on semi-decidability, that we can test if an element belongs to a set and get positive information to belong to a set. But if the element doesn't belong to a set, we don't get any information, because the part of the function being undefined is like you keep on waiting forever for an answer. You don't know that the answer is not going to come. You might just, for all you know, you might not quite have waited long enough. You keep on waiting. You never find out that the number belongs to the set. You just get bored waiting, basically. So if x doesn't belong to A. So if its partial characteristic function is a computable partial function. Okay. So far, all we've done is repeated definitions. Had before. But I do want to make a remark before we go on from here. So the terminology itself here, of computably enumerable, is in a sense already referring to the generativity notion of a set. The definition is about testability. And the definition I've given, this is, can we test an element for membership so at least we get the positive information of the element positive set. So the definition is to do with testability, but this terminology computably enumerable comes from the fact that we're going to discover later that such sets turn out to be exactly those sets for which we can list the elements of the set. Okay, and that's where the terminology comes from. So at the moment, the terminology is not really quite justified by this definition, but it will be later justified by a theorem saying this definition in terms of testability agrees with an alternative definition we could have given in terms of generativity. Okay. So having introduced those basic, or rather reintroduced, because we have them already, before going on and looking at the concepts, I want to consider an example of a set of natural numbers that's going to play an important role for us. And this is the set of natural numbers that corresponds to the halting set of words encoding Turing machines, or the accept language of words encoding Turing machines. So these basic sets we considered early on in the course that were decidable, that were not decidable, but were semi-decidable. So now we're dealing with sets of natural numbers. Such a fundamental set, a set that's semi-decidable, that is computably enumerable, but not decidable, that is not computable, is going to be very important to us. And we're going to take one of those sets that can be given with one of the simplest definitions. So maybe I'm going to keep this board as a split board. Because I don't need a wide board for the next part. So the halting set of natural numbers it's called K after Kleene, is defined by. So what K is going to be a set of numbers, and we want this to be kind of analogous to the sets of codings of Turing machines that halt on a suitable input. So we're going to consider a set of numbers. We want to consider those in a similar role to codings of Turing machines. Well, we can do that via, we know from the previous, not last week's lecture, but the lecture before, we enumerated the computable partial functions. And we can look at, instead of considering the Turing machine encoded by, we can look at the partial computable function, computable partial function encoded by E. And we simply want, this is like the halting set, so it's going to be those numbers E for which the function phi sub E, so the E-indexed partial computable partial function, halts on a suitable input. Doesn't matter too much what input we could give. We could give 0 here if we wanted to, but it turns out to be easiest for the proofs to give to apply each computable partial function to its own index. And we ask, is the set of those, so those indices for computable partial functions, such that the computable partial function is defined, that's like halting, on its own index. And the fact that we use the same E here just allows the proofs to be rather straightforward. So the first proof, which as you'll see is very straightforward, is going to be the proof of this proposition, which is that K is not computable. So it's no surprise now, at this point of the course, that this is not a computable set. So it's an undecidable set, and the proof is going to be very like other proofs we have given, essentially using diagonalization, but actually the diagonalization is already built into the definition of the set K itself. That's why we're applying the E-indexed computable partial function to its own index. That's like the aspect of diagonalization that comes into this not computability proof. So let's prove it. So let's suppose the contradiction that K is computable. Suppose K is computable. So computable means decidable, which means that characteristic function is a computable function. So that means that the characteristic function of K is computable, so it has some index. So let E be the index, be an index for the function. So assume K is computable. So that means that the characteristic function is computable. Sorry, this is kind of K. So it has some index. So what being an index means, i.e., the E-index partial computable function is the same partial function as characteristic function of K. Okay. We're also going to define a function. Actually, I don't know why I'm walking around with my notes in my hand, but at the same time not looking at them, because you can do this, but actually in the proof, I'm going to need an E, which is the index of something, but it's actually not going to be the index for this function at all. And we don't really need the index for that function. So let's forget that. I was on the autopilot, and then I had a glance at my notes, and I realized I was going the wrong way. So if K is computable, but that means that the characteristic function of K is computable. Definition of computability for a set is in terms of computability of the characteristic function. So the characteristic function is computable. So then also the total function h below. So you may have noticed that a lot of these proofs, we define a function h in the proof, and then we prove some properties of it. So also the total function h below is computable. Well, the idea of h is it's going to do something that we can't actually do, but we would be able to do it if chi k were computable, which is what we've assumed. So what? I keep on not looking at my notes. So our total function is actually going to be a partial function. But this partial function is going to be a computable partial function. So what this partial function does, h takes a number x, and it applies the characteristic function of k to x. And if that characteristic function comes out as 0, then h returns 0. Doesn't actually matter what it returns. It's like it's the characteristic function of k applied to x is 0. So that means if x does not belong to the set k, then we're going to return 0. But the important thing we're going to do is that, so we first test the total function characteristic function. So we first test the characteristic function applied to x. If it's 1, then we're going to not return. We're going to go into a loop. So we don't return an answer. And because h is computable, it's a computable partial function, it has an index. Let's call that e. So that e be the index of h. Or another way of saying that is that e be such that the e index partial computable function is h. So h is a computable partial function. So it's phi e for some e. And then we see that we get an easy contradiction because we look at what happens to phi sub e if we apply it to the index e. Well, we know that, so this is the same thing. So if we apply phi sub e to e, if that is defined, well, if and only if e belongs to k, by the definition of k. Okay, but e belongs to k, well, if and only if phi k of e equals 1, because that's the characteristic function of k. And that holds, so let me put that in, it's not actually in the notes, but let's be very thorough on the board. So chi k of e equals 1. And chi k of e is 1 if and only if h of e diverges. H of e doesn't return the value. So if and only if h of e is undefined. But h is the function phi, is the partial function phi sub e. So h of e being undefined is the same thing as phi sub e of e being undefined. So we've got that phi sub e, the e index partial computable function applied to e is defined if and only if it's undefined. So that's a clear contradiction. So the conclusion is k is not computable. So this contradiction shows that k is not computable. Okay. Okay, I'm back, and it's still recording. Amazing. So there was some Zoom outage, but it managed to fix itself. And that's the. So I just need to fix this. That's the first time I've ever witnessed Zoom fixing its own problem. But I think it was an internet problem, but it came back fast enough that everything was repaired. Right, so we're going to show that k is not it's computable. Sorry, it's not computable, but it is computably enumerable. We could do that directly, but it's more helpful to get a characterization of computably enumerable sets and to use that to derive that k is computably enumerable. So do I call this a proposition? The computable enumerability, but it's basically pretty much just an observation. So a set of natural numbers A is computably enumerable if and only if it is the domain of a computer partial function, a unary computable. So a computable partial function from natural numbers to natural numbers. So the computably enumerable sets are exactly the domains of computable partial functions. For every partial function has a domain of those numbers on which it's defined, and the computable ones, those sets that have domains, are exactly the computably enumerable set. And this is actually very easy. So if a set is computably enumerable, so left to right implication, if a set A is computably enumerable, well, a set is computably enumerable if its partial characteristic function is, but then it is the domain of its partial characteristic function. So it's simply the observation, this observation is simply that A is the domain of partial characteristic function. The other direction, suppose we have a computable partial function, we want to show that the partial characteristic function for its domain is computable. But you simply take the computable partial function you have and you simply run that function and change the values to 1 and you get the function back. So I've written that up in more detail in the notes, but for the sake of the lecture, I'm just going to call that easy, because if you think about it, it is easy, and it's not worth spending more time on now. No. Well, the exam, you can't ask me. So you mean the oral exam? You can't ask me about the written exam. That's to do with what you do with Deborah in exercise classes. Time on it in the lecture, you need to think it through for yourself, and you can look it up in the notes. And at that point, you should be able to repeat it in the exam. Anyway, let me carry on. Anyway, given this proposition, we now have the corollary. K is computably enumerable. And the reason for this is that K is the domain of the partial computable function that takes the number x and maps it onto the result of applying the universal computable function to the pair x. Remember, the universal partial computable function was defined. This was something we did in the last lecture. This was defined by it applies the x-index partial computable function to the argument y. This is the definition of the universal partial computable function. So this is replace x by e, we will be mapping e to the e's partial computable function applied to p, and k is just by definition the domain of that. Okay, so that's a computably enumerable set. Right, so we've still got 2 minutes till the break, so I just want to come on, focus. Right, okay. everything all right? Yeah, I'm going to break in 2 minutes. So what did I want to do? So characterize the computably enumerable set as the domains of the computable partial functions. And this actually gives us a very simple and natural way of enumerating all computably enumerable sets. W sub E, this is a standard definition, to be the domain of the E-indexed partial computable function. Remember, this was an enumeration of all computable partial functions. So since the computably enumerable sets are the domains, this means the domain of, so since the computably enumerable sets are the domains of the computable partial functions, this is an enumeration of all computably enumerable sets. So W0, W1, W2, W is an enumeration with repetitions of all computably, so C.E sets. Or another way of saying it is that the map from E to W sub E, which is a map from natural numbers, the total function, because every E is an index of the computable partial function. So this is the total function from E to what I'm going to call CE. This is the set of all computably enumerable subsets. So there are only countably many computably enumerable subsets. CE sets of numbers. So this is a total representation of the set of computably enumerable sets. We representing now in this course by numbers rather than words. There is a total representation of the set of computably enumerable sets. The important thing really is that this W sub E, that's, as I say, that's the standard notation, is giving us a way of enumerating all computably enumerable sets. So we've got now a numbering. We had last time a numbering of all computable partial functions. Now we've got a numbering of all computably enumerable sets. Okay, that's enough for this hour. So we'll start again at 3:50. Okay. So we've got the notions of computable set of numbers, in other words, decidable, and computably enumerable, in other words, semi-decidable set of numbers. Of course, any computable set is computably enumerable. Any decidable set is semi-decidable, trivially. And the converse doesn't hold, as we've seen throughout the course. Still, you could ask somehow, how much more general are computably enumerable sets than computable sets? And hopefully the following example will be illuminating but one can make formal definitions that quite easily give a formal version. I just wanted to make it intuitive. So let's consider the set of pairs of numbers for example, in the Turing machine model of the E-index partial computable function applied to E terminates in exactly k steps. So here we're applying phi e to e, but we're not just asking does phi e of e terminate, but we're giving a time bound, as it were, the number of steps that the computation wants to conclude upon. And hopefully you can got enough experience on this course to see that this is a decidable set of pairs. Because what you do, you've given your E and your K, you then you decode E to get the representation of the Turing machine that E represents. You run that Turing machine for exactly K steps, you simulate the execution of the Turing machine for K steps, and then you look, am I in the hold state or not? And if you are, then you say yes, and if you're not, then you say no, it did not terminate in exactly K steps. So this is a decidable set. Let's call it HIP. Let's call this L, but for no good reason. This is just for this lecture. Then K is the EK belongs to L. Okay, so set K, the halting set itself, differs from L in that we don't give a time bound. That's not a bound, it's even if we could work with a time bound instead, but we don't give a time. We simply, so we say, does it hold? So does there exist some number of steps for which it holds? And this turns out to be a quintessential, the quintessential way that one forms computably enumerable sets. Computably enumerable sets can all be viewed as searching for a number such that some decidable property holds, just like this. And that's the content of the next result. So the proposition says that a set, maybe I'll get my notes just so I write it in the same way. Also, so that I write it correctly, the way things are going today. So a set A of natural numbers is computably enumerable, CE, if and only if there exists a computable total function two-argument computable total function such that the number x belongs to A if and only if there exists a y such that, well, for some reason this isn't Z, oh, I know why. If and only if there exists a Z such that T x Z, or we could say equals 1, but in the lecture notes, so make it consistent, we say T x Z equals 0. The point is, we view T as acting as a test on pairs of numbers, and actually viewing 0 as the true result in this case, as the truth value in this case, but it doesn't really matter. And an A is the set of those x's for which there exists a Z such that the test function gets assigned to 0. So that's generalizing this example here, where here the little t function would map E and K to 0 if the computation by sub E of E terminates in exactly K steps and would map to some other number otherwise. Okay, but every point is every computably enumerable set can be written and can be obtained function on pairs and searching for number testing on pairs. And moreover, whenever you have a property that's put in this form, it is a computably enumerable set. Okay, so that's a nice little characterization. So let's prove which direction. Let's prove the easy direction first, which is the right to left direction. So we're supposing there exists such a t. And we want to see that this set A is computably enumerable. Well, actually, that's very easy because A is the domain of the function that we're written using the terminology of the notation of like 3 lectures ago when we did primitive recursion, minimization, and so on, is written mu t. Another way of looking at that, this is the function, i.e. the function, this is the function that takes an x and maps it to the I such that t x y equals 0. So this is maybe a more readable way of writing it. But by this I mean this function mu t is defined using minimization. It's simply map x to the smallest value y such that txy equals 0 if such a y exists. For it to be consistent with the notation above, I might say the smallest z. Doesn't make any difference, of course. If such a z exists, otherwise this function, this partial function, undefined. And because t is a total function, we don't need to worry about the other aspect of minimization, which is that all values until you find the one you're looking for have to be defined. Because that's automatic because t is a total function. Okay. So essentially the idea is we've got our total function t, and we just need an algorithm whose domain is A, and that algorithm is search for a z. That's the informal version of that proof. Okay, so that's the easy direction. The tricky direction . So the tricky direction is the left to right direction, because that way we have to find this function little t. But actually, it's not that hard because we've done the hard work already. A couple of lectures ago, I don't quite remember which lecture it was in, but you might not quite remember all the results from now because I don't think we've done them in the exercise class yet. But if you remember, a couple of lectures ago, we had Kleene's normal form theorem. And Kleene's normal form theorem said that any computable partial function could be computed via a specific combination of minimization and primitive and a certain number of primitive recursive functions. So by Kleene's normal form theorem, well, there's a line above here which I missed, which I didn't put in, which is suppose A is CE. So then let E be such. So if A is computably enumerable, then it's the domain of a computable partial function. So let E be an index for such a computable partial function for which A is the domain. So let E be such that A is the domain of phi sub E. So that's the missing line above. And now by Kleene's normal form theorem, the domain of phi W, well, let me see how I've written it in the notes. So there we have that X belongs to the domain to A, which is the domain of phi sub E. If and only if, well, Kleene's normal form theorem says that phi sub E is defined on X if and only if Kleene's D function applied to the values E and X equals 0 for some value Z. So if and only if there exists a Z. So it was already 2 weeks ago, so you might not quite remember all the details here. But the idea here is that Kleene's normal form theorem said, give me the index, that's the code for a computable partial function. Give me an input X, that's E. Give me an input X for the partial computable function. And give me a Z, which is supposed to encode the whole configuration history of a computation that of Turing machine E on input X, and Z is the whole configuration history of the computation all the way through to the halting configuration. And the T predicate is 0 if and only if E, X, and Z conform to those criteria, satisfy those criteria. So you can only find such a Z in the case that phi of E halts on X, because the only such Z which you can use for this purpose is a Z which is a huge number encoding the whole configuration history of a successful of a terminating computation of the Turing machine for E on input X. Okay, but if you look at the statement of the theorem from the notes 2 weeks ago, I mean, this is just immediate, but this is part of the statement of the normal form theorem. But given this, well, we simply say T xz is defined to be T E X Z. And that does the job. So that is a computable total function. In fact, it's a primitive recursive function, and it does the job required. Okay, so it looked like it was going to be tricky, but the tricky part was done 2 weeks ago. But the tricky part today is remembering what we did 2 weeks ago. Even for me. Last week was such a sort of big event that it's kind of a barrier to remembering what went before it. Okay, so I'm going to, this is going to be very useful, this little characterization of computably enumerable sets. I'm going to start immediately with an application that maybe would be useful to see the whole board for over here rather than using that board. So the next result's a nice result which we may have already discussed in an earlier exercise class more informally. And it's a way that the computably enumerable, that is semi-decidable sets, relate to the computable sets. And that's the wrong remote control. We need this one. That's good. So the result is, oh, it's even down as a theorem in the notes. Set A of natural numbers, I'll just write A, is computable if and only if both A and its complement, which I'll write A bar, so that's just defined to be the set difference. So all those natural numbers not in A are computably enumerable. Okay, so a computably enumerable set does not need to be computable. But if its complement is also computably enumerable, then it is computable. So one direction here is easy. If a set is computable, well, then it's obviously computably enumerable. That's a weaker property than computable. It is also obvious that the complement is computably enumerable because the characteristic function were computable, and you can simply invert the 1 and 0 on the characteristic function. So the left to right direction is easy. Now the right to left direction has an informal proof. Sorry, I'm just need to adjust this again. The right to left direction has an informal proof, which gives you a nice idea for why it's true. But I'm also going to give a more mathematically precise proof using well, sorry, not that, but the lemma that I've rubbed off the board. So suppose a set and its complement are both computably enumerable. We want to show the set is computable. So we want to compute the characteristic function of the set. So we're going to do that by the following algorithm. Take a number as input, and we want to return 1 if it's in the set, and 0 if it's not in the set. Well, we've got partial characteristic functions, both for the set and its complement. So we're going to run computations for these partial characteristic functions in parallel. And because the number will be in one of the two sets, either the set or its complement, one of those parallel algorithms will eventually halt with the answer, yes, that number belongs to me. In fact, only one will halt because obviously the complement and the set itself are disjoint. So you just run the algorithms in parallel and wait for one to halt, and then return either 1 or 0, depending on whether it was the partial characteristic function of the set itself, that's 1, or the partial characteristic function of the complement set, then you return 0. That's a bit informal. That's a kind of informal use of Church's theorem. Sorry, not Church's, of the Church-Turing thesis, if you like. You can see there's a kind of algorithm there, but I haven't made that precise. We wanted to run that on a Turing machine. Well, Turing machines are not parallel, but still you can do that, because you can kind of interleave those two computations instead. So rather than running them in parallel, you do a step of one, a step of the other, and go back and forth until eventually one halts. So we can make it completely precise that way, and we could do that, or we could say, well, we know how to make it precise, and we've proved the result. So both those, so you've now got two proofs, essentially, the informal proof plus the idea for how to make the informal proof precise. I'm now going to give you a third proof, which is just doesn't require anything else to make it precise. It's just immediately precise using the lemma that we had previously. The only thing is, it's not so easy, the informal idea of running in parallel is very easy to visualize. Now you have to follow the symbols. So perhaps it's less easy to understand. So anyway, to do the version I'm going to write up is this one. So suppose A and its complement are both C. So that is, we've got partial characteristic computable. Hello? Oh, sorry. Okay, there's not a. So was there some? No, it's fine. Yeah. No, it wasn't from here. No, yeah. Sorry. Well, I don't know what's going on, but it's probably better than I don't know. Sorry. Anyway, now I'm lost. So if they're both CE, then by the previous lemma, we can view both of these sets as searches for a z to which we test, for which we can do a computable test for pairs of numbers. So by the previous lemma, which I might not have called the lemma, maybe I don't remember what I called it in the lecture, by the previous result about there exists a function little t, I'm going to call these functions little s here. So there exist computable functions s and s prime, which are total computable functions in 2 arguments, such that x belongs to A if and only if there exists a z such that s x z equals 0, and x belongs to A prime if and only if there exists a z such that s prime x z equals 0. So this is still x belongs to, sorry, this is the complement of A if and only if there exists a z. So we've got these total functions by the previous result such that membership of the computably enumerable set can be tested by searching for a certificate, little z if you like, and applying a testing property which is a total computable function. So then, if both these functions f and f prime are computable, then the function below is also computable. And this is the function g of x is the smallest z such that the minimum of s of x z and s prime of x z equals 0. So the idea of using the minimum here is we just need one of these 2 things to be 0. And the point is this is our way of running things in parallel. We want to find just some z that either if s of x z is 0, that z is a certificate that x belongs to A, and if s prime of x z is 0, then that z is a certificate that, sorry, I said x belongs to A, and x prime, and then x belongs to A, and if s prime of x z equals 0, then it's a certificate that x belongs to a complement of A. So it's computable and it's total because every x belongs to either A or its complement, and depending on which one it belongs to, there will be a witness z that gets such that either s of x z or s prime of x z equals 0. So we can compute the characteristic function of A by the characteristic function of A applied to a number x is 1 if g of x equals 0 and 0 otherwise. Because, hang on, no, that's not right. So what we want to do is if s, x, and g of x equals 0 and 0 otherwise. Because this function returns a z that will uniquely either witness that x is in A or this x is in the complement of A. Here we test to see if that Z witnesses that x is in A, and if it doesn't, well, it must have witnessed that x is in the complement of A. Okay. And as a result of this, let me just observe a little corollary. I'm going to squeeze it at the bottom of the board. I mean, we shouldn't do this normally, but such a small observation. So for our halting set K, we showed that K is not computable, but it is computably enumerable. So therefore, by this result, it's clear that the complement of K is not computably enumerable. So the corollary, complement of K is not computably enumerable. Right. So far, I haven't addressed at all what I said I was going to do. Well, I've addressed one side, what I said at the beginning. So we were talking about, at the beginning I was talking about sets and the kind of interplay between testability. And we've been talking about testability the whole time here. Characteristic functions are like testing elements to see if they belong to a set. Partial characteristic functions is the same, you're testing elements. But the other aspect was generativity, and we haven't considered generativity at all. So to address generativity, we're going to get that now immediately in a major theorem that gives an alternative characterization of computably enumerable sets. If so the theorem is a theorem that says, well, it's going to characterize computably enumerable sets. So this says the following are equivalent for a set A of natural numbers, or any set A of numbers. So statement one is that A is a complement. So we want to characterize the computably enumerable sets. So remember, computable enumerability is defined in terms of testability, so semi-decidability. But the other aspect we wanted to look at was generativity. And we're going to get that now. So you can think you can generate the elements of the set if you have a computable function that's going to list the elements of the set as its output. So the computable function pi to 0 is the first element is an element of the set. The function pi to 1 is another element of the set, and so on. And we want to get the whole set as the image of the function. So what we're going to do is we're going to do this in quite a strong way. We're going to say that A is the image, or range is another word, English word for this, you know, the set of all result values of a total unary, a single argument, computable function. So that's almost equivalent to A, B, C, E. There's actually something wrong with this statement. It's not quite equivalent at the moment. Can anyone see? There's one set that is computably enumerable that is not the image of any total unary computable function. Sorry? Yeah, sorry, I can't see who's saying that, but anyway. The empty set. Indeed, the empty set. So the image of a total function is necessarily non-empty, but the empty set is computably enumerable, it's semi-decidable, just by its partial characteristic function is the everywhere undefined partial function. So or A equals the empty set. That. Thirdly, rather than saying A is the empty set, we could say that A is the image of a computable partial function, because then the empty set can be the image of a partial function because it can be the everywhere undefined partial function. That turns out to be equivalent. So A is the image of a partial. Sorry, let's put them in a sensible order. A unary computable partial function. And I'm going to put unary in brackets here because unary can actually be replaced with any arity and it's the same, exactly the same result. You get exactly the same characterization. I'm not going to talk about other arities in the proof, but just to mention that. That's the reason I'm putting it in brackets. Okay, so I think this is a nice result because it's testability, at least in a weak sense of the semi-decidability. So we get an affirmative answer if the number belongs to a set, but we don't get any information if it doesn't belong to the set. The testability in that weaker sense, the semi-decidability sense, is the same as being able to enumerate elements of the set in a computable way. So testability is generativity. And this, the two statements 2 and 3 here are the motivation for the terminology computably enumerable set. That's where that comes from. Right. So I think I'm going to leave the proof of this until after the break. It's a nice proof. Well, I mean, it takes a proof. This is not an immediate statement. But rather than going to the proof now, for the break, I want to look at some other aspect of this, which is using this, we can define a second enumeration of the computably enumerable sets. So we have a second enumeration of the computably enumerable sets. Which is, we've already done the WEs, but the standard notation for this is capital E, sub E, so little e, as you will have noticed, is the standard letter one uses for indices of computable partial functions and sets and things like this. But E sub E is defined to be the image of the unary computable partial function I sub E, of the E index computable partial function. So once again, the E sub 0, E sub 1, E2, 3, and so on, enumerates all computably enumerable sets. And again, we can view this as we have a total representation mapping any number, little e, onto E sub E, which is a surjective function from natural numbers to computably enumerable sets. In fact, we have in total 2 total representations. one that maps any index e to the image of the e computable partial function, and the one that maps any e to the domain of the e computable partial function. It's a nice fact which you can think about, not completely straightforward. The nice fact that these are equivalent representations. I think that's going to be done in the exercise classes at some point. So it doesn't matter which one you use, but see, sometimes it's more convenient to work with domains and sometimes to work with ranges. These are equivalent images, which is the same as ranges. These are equivalent representations. And just before the break, let me put this. Let me put this. Let me put this a bit closer here. So before the break, just to say, when I was learning computability theory the first time, I used to get these muddled up. I could never remember whether E sub E is the image and W sub E is the domain, or vice versa. Then I came up with the following mnemonic. So just in case it might be helpful to you, if you feel that you need to remember. So my mnemonic for this is that here we've got domain, and domain has got an N in the middle, and if you rotate it by 180 degrees, it's a W, or close to a W. And here you've got image or range, it doesn't matter. Domain does not have an E in it, but image does have an E, and so does range. So it's not very useful, probably not very useful, but anyway. It does help me, and it did help me when I was a student. Okay, well, it's 5 to 4, so let's have a 15-minute break and start again at 10 past 5. Okay. The network seems to have been a bit more reliable recently. Okay, so I want to begin this last part by proving our theorem, the equivalence of the testability view of computable enumerability with the two different generativity views, one in terms of the image of total computable functions and one as the images of partial computable functions. So 3 statements are equivalent. We're going to do going round the circle proof. Let's get the easiest case out of the way first. Okay. Yes, fine. Certainly not today, forgetting your own brother. So the easy implication is 2 implies 3, because if A is the image of a total computable function, then it's A for Teorija the image of a partial computable function, because every total function is partial. Every total computable function is the total function is a partial function. A for Teorija, so for stronger reasons. So that deals with the case that A is the image of a total computable function, or the case of the empty set, or the empty set is the image of the everywhere undefined function. So, and the empty set is the image of the everywhere undefined partial function. Okay. So that's easy. The next easy implication is 1 implies 2. I mean, the next easiest. 1 implies 2. So we assume that A is computably enumerable. In other words, that it is the domain of some computable partial functions. And we want to show that either A is empty or it's the image of a total unary computable function. So let's just assume we have a non-empty set that's computably enumerable and deal with the non-empty case, because that's the only interesting case. So suppose A is CE and A non-empty. So because A is non-empty, it contains some element. So let's A0 be some little A sub 0 be some chosen such element.
Can you swap the camera?
Sorry, thank you. So we're going to choose some element little A0 belonging to A. And because A is computably enumerable, by our lemma that characterizes computably enumerable sets is exactly those sets one gets via searching for a Z such that we can test some property of pairs with that set. So by the earlier lemma or proposition, I don't remember what I called it in the lecture, it's lemma 7.6 in the notes, not that it really matters. So by the earlier result, there exists a total computable S, binary function on natural numbers, such that an element Y belongs to A, if and only if there exists a Z such that S, Y, Z equals 0. So we're going to use this we want to display A as the image of a computable total function. So I'll just write it down and explain it as we go along. So A is then the range or the image. What do I use? I say image, and I mean they're synonyms, image and range in this sense, is the image of the total computable function that maps any number X onto, well, the idea is we're going to interpret X as a pair, Y, Z. So we have our pairing function on natural numbers. We interpret X as a pair Y, Z. And if S applied to that Y, Z is 0, then we found an element Y that belongs to A. Okay, so we're going to return Y in the case that X equals P, Y, Z and S of Y, Z equals 0. And because every pair of numbers, every number X is interpreted uniquely, so remember this is our pairing function that we had in an earlier lecture, which is a computable bijection from pairs of natural numbers to natural numbers. So because every X is uniquely of the form P, Y, Z for a unique Y, Z, this way we're going to test all different pairs Y, Z, and whenever we find one that is witnessing that an element Y belongs to the set A, we return that element, Y. And in the other case, so when we can always, for any X, we can find the unique Y and Z such that this is true. And in the other case, that S applied to Y, Z is not equal to 0, so that's the otherwise case. we still need to return some element of the set A because we want it to be a total function. So we need to return an element, and we want A to be the image of the set, so we want the element to belong to A. That was our reason for needing this element A0. So in that case, we return the element A0. Okay, and we're done. Okay. So it remains to do 3 implies 1. The main difficulty here, so we need to turn an image, so we're given a computable partial function. It has its image. We want to find another computable partial function that has that image as its domain, essentially. That will do the job because we earlier on characterized the computably enumerable sets as the domains of computable partial functions. So to do that, we need to again take our memories back to 2 lectures ago and again remember this Kleene's normal form theorem, I'm afraid. So once again, I shall talk you through it. I shall talk myself through it and at the same, hopefully in such a way that I'll be talking you through it at the same time that I'm talking myself through it. So I did understand it in the break between the lectures, but 10 minutes have since passed. So it's not particularly complicated. We just need to. Right. So we want 3 implies 1. So we've got that A is the image of a computable partial function. So suppose A is the image of the E-indexed computable partial function. Right, so remember Kleene's normal form theorem, or we will in a moment. And I'm just going to say then the function, which is a total function, binary function of natural numbers below, is computable. In fact, it's primitive recursive. So this function is going to be defined as follows. Take a pair xy and return either 0 or 1. And 0 we're going to return in the case that the Kleene function applied to E, x, and z equals 0, and w equals u of z. So t we've already seen in this lecture. It was one of the functions in Kleene's normal form. It's sort of the one that says t e x z equals 0. Remember, if the z is the encoding of the whole sequence of configurations leading to a halting configuration of Turing machine indexed by E run on input x. And U then is another ingredient in Kleene's normal form theorem. It's the primitive recursive function that, given the whole sequence of configurations, extracts the number on the output tape. So it gives the result value of that computation, of that sequence of Turing machine configurations. We return 0 if these hold where y is considered as a pair of x and z. Is this right? It should be w here. That's better. So here we're saying interpret y. So we're essentially, we've got a 2-value function, but we're essentially interpreting the inputs as w, x, and z. We're essentially given 3 inputs, w, x, z, because we're interpreting y as a pair of numbers. We're given 3 values, w, x, and z, and f will return 0 in the case that the function of which a is the image So S applied to W, X, and Z will return 0 in the case that Z is an encoding of all the computation of the function of which A is the image applied to the input value X, and W is the output value. So these requirements together, that these imply that W is the result of applying phi of V to X. Because here we extracted Z, all the sequence of configurations of the Turing machine computing phi of V on X, and then W is extracting the value from that sequence of configuration. And otherwise, we're going to return 1. And the point is that W belongs to A if and only if there exists a Y such that S of WY equals 0. And that means that A is computably enumerable according to our characterization result earlier that characterized computably enumerable sets by searching for values using a test function on pairs. But then, so thus, A is computable by earlier result. Which I wish I'd given a name to, but I keep on referring to it as the earlier results. So that ends the proof, except I haven't completely talked you through this if and only if here. And as I said, I'm going to have to talk myself through it. So let's just see if it. This is. I mean, it's not particularly tricky, but anyway, let's see. So suppose W belongs to A, then there exists an X because A is the image of phi of V. There exists an X such that W equals phi of V. Okay. Moreover, there exists a Z that is the encoding of the whole Turing machine of phi, computing phi V on X, the encoding of all the configurations. So then there is a Y that pairs up X together with that Z encoding all the configurations of the Turing machine, then all these things are satisfied. This holds because Z is encoding all the configurations of the Turing machine that's computing phi of V on X. W equals U of Z because W is indeed the result of phi of V on X. So we extracted that result from the sequence of configurations. And I mean, just to begin with, I was saying, well, Y is the pair in X, Z. So that direction is true. In the other direction, if there exists a Y, well, you basically reverse that argument. I mean, I could talk you through it, but it's literally reversing what we've just done. But if there exists a Y such that this holds, then that Y is forced to be, by this definition, a pair consisting of an XZ, where Z is the encoding of all the Turing machine configurations for the computation of phi of V on X. And therefore, because of that, the W has to be a result of phi of V on X, and therefore it's in the image of phi of V, and therefore it belongs to A. So there you go. It does all work out, and you can have a look at the notes which are online, and you will see it.
It's probably not completely enumerable.
Well, I did indeed. Thank you. Otherwise, we would have a miracle. So, yeah. Right, good. So this is a characterization of computable enumerability now in terms of two different ways that we can generate the set, either as the image of the computable partial function, or as long as the set's non-empty. Obviously, there might be some repetitions, but as the image of a total computable function. So what about representing sets of images without repetitions rather than potentially with repetitions? And what about, can we list also the numbers in order? So here, we just got the image of a total computable function, but it might go, the computable function might assign 3 billion to 0, and then 6 to 1, and so on. So it might just jiggle up and down. It doesn't necessarily need to be sort of going in a monotone increasing way. So is there a way of sharpening this so that it's an image of a better behaved function? Well, actually, it turns out that if you take a natural sharpening, you end up characterizing the computable sets in terms of generativity rather than computably enumerable sets. So I want to do that and then observe one consequence of that characterization, and then we'll be done for the day. So nothing is quite as involved as what we've just done. Hang on, I didn't mean to do that. So I'm going to do the following are equivalents. But this time we're going to have A is computable. Again, we're going to have being computable in this time not being enumerable. It's again going to be the image of a total, this time user is important. Well, let's not even write it down. It's so important I won't write it. Because it's going to be implicit in what I say next. It's a total, well, actually, let's put this word. It's going to be the image of a strictly increasing total computable function. So that, I think you'll agree, that's a very natural condition to put on the computable function. So if the function is f of 0, so strictly increasing, I think you all know what that means, but f of 0 is strictly less than f of 1, is strictly less of f of 2, and so on, okay? So A is the image of a strictly increasing total computable function. Or we've again got a missing case here. So what's the missing case this time? Well, obviously we still don't include the empty set here, but there's a whole family of computable sets we don't include. Can anyone see what they are? Sorry? Finite. The finite set. So if you've got a strictly increasing total function, its image is always infinite, obviously. So every finite set is computable, because for a finite set, you just need to do a finite number of if then else statements to define the characteristic function. So one of the two holds, so either A is finite or every infinite computable, for infinite sets, computability is equivalent to being the image of a strictly increasing total computable function. Okay, so let's prove this. It's not as involved as what we did before, and I'll try and keep it to high. Well, it would be quite involved to do it very formally. I'm going to keep it at a more high level now. Fortunately, we've only got 2 statements here, so the nice thing is it's a very natural characterization of computable sets in terms of how one can generate them. So computability is testability with a proper 0-1 test, a Boolean test, yes or no, and this is generativity by a nice way of generating the elements of the set. So for 1 implies 2, so let's suppose A is computable and infinite. It's easy that every finite set is computable. well, anyway, actually that's relevant to the other direction, not to this. So suppose A is computable and infinite. So we need to exhibit A as the image of a strictly increasing total computable function. So I'm going to define the function f by giving an informal algorithm, and you can see how we can compute it. Then I'm going to appeal to Church's thesis, the Turing thesis, in the non-essential way that I referred to last week. So one can easily, one can put in the work and translate this to a proper definition, but at this point, let's just convince ourselves by showing we can compute the function. So I'm going to also define the function on -1 for convenience. I'm going to define f of -1 equals -1. And then for x greater than equal to 0, define f of x. It's going to be, that's an x. Don't quite know what happened there. F of x is the smallest. So we're defining for the biorecursion. We've already computed. We can already compute f of x -1. We've defined f on all values smaller than x. Then we can consider the smallest natural number greater than f of x -1, such that the characteristic function of A applied to n equals 1. The point is, we want f to be a strictly increasing function. We've already got the previous value f of x -1. We know that the next value we need to return needs to be a bigger value. So we simply start from x -1, f of x -1 plus 1. Test it and see if it's in our set A. If not, we go for f of x -1 plus 2. Test that, and so on. Then we just count up the numbers until we find one that satisfies the property. And because it's an infinite set, because A is an infinite set, eventually we're going to find a number that satisfies the test. And when we get there, we return that value, that is f of x. Okay? So I think you can easily see how to write a program for this. Therefore, it's computable. And it's easy to, hang on, yeah. Yeah, so f restricted to the natural numbers, so we forget about -1, having made the definition, is a strictly increasing total computable function whose image is f. So the other direction suppose then that, well, it's easy to see that every finite set is computable. I already argued that. Just do finite number of if then else checks to see if a number belongs to the set. So we only really need to deal with the case that we have the image of a strictly increasing total computable function, and we need to show that that's a computable set. So if the 2 implies 1, let me be consistent with the notation in my notes. So, so let f be a strictly increasing total computable function. we want to show that its image is a computable set. So we need to define the characteristic function of the set. So define we're going to define the computable function g by g of x is defined to be 1 if n equals f of x, where x is the smallest number such that f of x is greater than or equal to n, and 0 if n is not equal to f of x, where all the above. The idea is, given an x, we find the smallest hang on. Yeah, that doesn't make sense, right? G of n, that's better. So given an n, we search through the numbers, x equals 0, x equals 1, x equals 2, f is a strictly increasing function. So eventually we will get to an x such that f of x is greater than or equal to n. We stop at the smallest x for which that happens, and if f of x equals n at that point, we return 1, and if it's not equal, we return 0. So it's a very simple algorithm, and because f is strictly increasing in total, this is a total function. So because f is strictly increasing in total, and total g is a total function, it's clearly computable. It's a total computable function. And it's also clearly the characteristic function for A. Oh, sorry, and G is the characteristic function for the image for A, where A is the image of A. Because you return 1 exactly when n lies in the image of F. Because if you go past, if you once get to the smallest x greater than or equal to n, and it's not an f of x, so that f of x is greater than or equal to n, is not actually equal to n, you can never for any other x find a value that's equal to n, because the function f is strictly increasing. Once you've gone beyond n, all values remain beyond n. Okay. So actually, not a difficult proof of this characterization, but I think it's a very nice statement, because again, it's another example of this agreement between the two notions we're thinking about, of goodness, of ways of having a handle on this set of numbers, testability, here the definition of computability, and generativity, here being able to generate a set as the image of a very nicely behaved computable function. So just to end with, it's only going to take 5 minutes. I'm going to just observe one nice and not completely, if you didn't have these results, this would not be an obvious result, but it follows very straightforwardly from what we've got. This is a corollary, which is every infinite computably enumerable set, that's a semi-decidable set, so every infinite CE set has an infinite computable subset. And the proof's written down a little bit more formally in the notes, but I'm just going to give you the proof idea. So the proof idea is let A be an infinite computably enumerable set. So it's a computably enumerable set exhibited as the image of a total computable function. So there exists a total computable function whose image is A. And the idea is to cut this down to a strictly increasing function. So basically, you can view a function, a total function, as a sequence of numbers, namely f of 0, f of 1, f of 2, f of 3, f of 4. And we've got an infinite image here. So we simply go through these numbers, accepting a number each time it's larger than the previous number. If you ever get something smaller than what you've already accepted, you just ignore it and go on until you get something bigger than what you've got so far. So you basically cut down the starting total computable function to a subsequence that is a strictly increasing subsequence. So extract in a computable way, and it's very easy to do. I mean, I think at this point in time, it's enough to have the high-level idea, and you can look at the notes or think about it yourself. So extract a computable, strictly increasing function as a subsequence in inverted commas, because, you know, well, anyway, a total function is a sequence, a subsequence of the original one. Yeah, so suppose we had sort of at 0, so suppose we had 7, 2, 5, 9, 1, 100, 6, 25, 314, 79, or so on. So this is the original function. This is the value of 0, 1, 2, 3, 4, 5. Then our new function where we take 7, 2 smaller, 5 smaller, so ignore them, we take 9, 1 smaller, we take 100, 6 is small, 25 is small, we take 314, and so on, because the image is infinite, you're again always guaranteed to eventually get to a larger number. So you again get a total function here. Okay. Good. So that's everything for today. The network has stopped being problematic for the last part, which is good. I'm going to stop the recording now.